In this video, I'll continue the discussion of collision detection in Havok Physics. In the previous segment we covered shapes, and in this one I'll talk about some of the ways that you can tweak the behavior of the collision detection algorithms and their output. Collisions occur when two shapes overlap, and to describe that overlap, collision agents generate contact points. A contact point consists of the position where the collision occurred, the normal, and the depth of the overlap. We need the normal because it tells us which direction is away from the collided surface, and that's the direction in which force must be applied to push the bodies apart. You can visualize contact points using the VDB. In this simple demo, we're just going to drop a box on a slope, and when it hits, blue arrows appear where they collide in the VDB. These show the position and normal of the contact points, so notice how they point up and out from the slope. The contact constraints apply impulses at the position of each arrow in the normal direction in order to prevent the box from penetrating the slope. As the box slides down the slope, the contact points remain, applying upward force against gravity. When the box falls off the slope, the contact points are removed. Note that in order to see this, I've turned on the contact point viewer, which you can use to show or hide the points. Choosing a contact position and normal is complicated, and in certain cases it's not obvious what the correct normal is. Consider a landscape mesh. We want it to be like a continuous surface where the normals always point up and away, but it's really represented as a collection of separate triangles. Triangle collision normals don't always point away from the face, they can point out from the edges as well. This means that objects sliding along a mesh can get contact normals that point sideways towards adjacent triangles, rather than up and out of the mesh, and that can push them in unexpected directions. To address this problem, Havok uses a technique called welding. It can analyze a mesh to find connected triangles and snap their collision normals to face outwards. This demo shows the difference. I've set up two identical meshes, but one is welded and the other is not. When I slide a box along each of them, the box on the welded mesh moves smoothly, while the box on the unwelded mesh gets knocked off course. If we step through to get a closer look, we can see that it's colliding with this triangle and getting a sideways pointing normal. Enabling welding is pretty simple. We just call a Havok utility function to set up the data for us. We pass in the mesh and the mop that wraps it, along with the vertex winding direction. And the reason that we need the vertex winding direction is that the normal could point in either way out of the triangle face, and we need to know which one is out. Another problem you might encounter with meshes is their thinness. By default, triangles are infinitely thin, which makes them especially prone to the bullet-through paper problem, where a fast-moving object crosses through a thin object in a single step without colliding. To help address this, a particular type of mesh called the HKP extended mesh shape supports triangle extrusion, which gives volume to triangle shapes. This demo shows how it works. Again, we have two identical meshes, and the one on the right is extruded. You can see the little bit of extra depth. And we have several spheres ready to be launched at each one at high speed. When I let them go, the faster ones go straight through the mesh, while the extruded mesh catches them. Since they move so fast, I'll step through, and you can see how the extra thickness allows us to detect more collisions. To set this up, we just have to specify which direction the triangles are extruded in and how far, in this case straight down by 0.5 meters. Note that I'm setting this on a triangle subpart, which represents a subset of the mesh's triangles, so it's possible to have different regions of the mesh with different extrusions. Extrusion helps prevent objects from flying through meshes, but deep penetrations have negative consequences for all types of shapes, even when we catch them. That's because they can cause TOIs, which are expensive to resolve. TOIs will be explained in more detail in a future video, but for now we'll talk about some tweakable settings that you can use to prevent them from happening. One of them is Convex Radius. This can be set on boxes, cylinders, triangles, and convex vertices shapes to add an extra shell of thickness, and the idea is that if you set the radius to x, then the shell will include every point that is within x meters of the original shape, although different agents interpret radius slightly differently. These shells can collide, but their collisions are resolved in a less expensive and less exact way than direct collisions between shapes, so often when two bodies bump into each other, their shells will deflect before they can incur a costlier computation. Note that spheres and capsules, the other two basic shapes, already have a radius as part of the normal shape definition, so there's no need for them to have a separate value. To visualize the convex radius, this demo shows several convex vertices shapes with different radiuses in green. Note that while the smallest has the default radius, the others are larger than you would typically use in practice. Also, the visualization is just an approximation. In the simulation, the edges are actually rounded, which is why the green box goes through the ground slightly. Finally, note that the shells do collide with each other. One downside to increasing convex radius is that objects will contact each other when they're visibly separated. If the radius viewer weren't turned on in this demo, we would just see boxes floating in the air. You can mitigate this using the HKP Shape Shrinker class. This will shrink an input shape and then use the convex radius to pad it out to an approximation of its original size, so that the modified shape still matches your visual representation. Another way to avoid deep penetration is the world's collision tolerance setting. This determines how close two shapes must be to have contact points. A non-zero tolerance means that bodies will apply collision impulses to each other before they really overlap, but unlike collision radius, it does not prevent them from eventually coming to rest with no space between them. This demo shows an example. I've set the collision tolerance extra high just for illustration, and the box gets a contact point with the ground long before they actually touch. And it tilts from the impulse being applied, but it still falls all the way to the ground before it comes to rest. Collision tolerance is a performance trade-off. It slows objects down before they overlap, which prevents deep penetration, and it also prevents the simulation from having to repeatedly destroy and recreate contact points for objects that stay close to each other and touch periodically, like a box settling or sliding on the ground. However, it also expands AABBs. If it's set too high, it will increase the number of broad phase overlaps, causing more narrow phase work and more contact points. Normally the default value of 0.1 meters is fine. All of the settings that I've covered so far tweak the way the collisions are detected, but often it's necessary to control whether objects are able to collide with each other at all. For example, you might have particle effects in your game that should bounce off the landscape, but that are too computationally expensive to collide against all of the dynamic objects. Or you might have a ragdoll whose adjacent limbs overlap and shouldn't collide. To manage this, Havok has collision filtering. Every shape used in collision tests can have filter info, and collision filters can check a pair of filter infos to decide if the objects can collide with each other. If not, then the collision test fails without checking if the shapes are really overlapping. Once a collision pair is filtered out, we can avoid doing any more work on it, so the filters run at every phase of collision detection in order to reject pairs as early as possible. Note that filtering can be used with asynchronous queries like raycasts as well. It's better to use filters than to cast against everything and then selectively pick through the results, because the filters make it possible to skip doing work to generate results that aren't needed. You can write your own collision filter, but Havok provides a default general-purpose implementation called HKP Group Filter that covers most use cases. The group filter offers two ways to control collisions between objects, and those are layers and groups. In this diagram we have a bunch of rigid bodies, and each one is color-coded by its layering group. The layers are pretty simple. Every object is on a layer, and collisions can be disabled between layers pairwise. Since the ragdolls and the floor are on different layers, we could disable collisions between layers 1 and 2 if we wanted the ragdolls to fall through. If we wanted one ragdoll to fall through and not the other, then we can move one of them to a third layer. However, there are only 32 layers available, so it's important to conserve them. If we had 32 separate characters, it wouldn't be possible to filter all of them against the ground independently using layers. For more fine-grained control, we need to use groups. Objects in group 0 are filtered using layers alone, but for non-zero groups it's a bit more complicated. By default, two objects that share the same group will collide with each other regardless of what layer they're in, but it's possible to specify a subset of the group to not collide with. Each object belongs to a subgroup within its group, and can choose a subgroup to disable collisions against. In the diagram, groups are used to prevent ragdoll limbs from colliding with the torso that they're connected to, which is commonly done for stability. Now if we try to do this by putting torsos and limbs on different layers, then one ragdoll's limbs would go right through the other ragdoll's torso, so that wouldn't work. If we created a separate pair of layers for each ragdoll, then we would run out of layers too quickly. But there are thousands of groups available, so we can create a separate group for each ragdoll, and then use subgroups to disable collisions between the torso and the connected limbs. This chart shows the logic that the group filter uses. Whenever two objects are in the same non-zero group, we use the subgroups to determine collision filtering. The rest of the time, we use layers. Layers are best applied to broad classes of objects that shouldn't collide, while groups are better suited to control individual systems that you might create many instances of. Let's take a look at how filtering is set up. In this demo, I've put each of the boxes on different layers. Collisions are enabled between yellow and red, but I've disabled them between yellow and blue, so the two boxes go right through each other. In the code, when I set these bodies up, I set their layer in the HKP rigid body C info. Layering group information is packed into a 32-bit field, so I use the calcFilterInfo utility function to figure it out for me. In this case I'm just setting a layer, but this function can take additional arguments for group info as well. Next I create the group filter, I tell it which layers I don't want to collide with each other, and I set it on the world. Tweaking collision detection settings will help you get good performance and stable behavior from your game. As you've seen in this video, it helps to know the details of how the simulation really works, so there's lots more information available in the docs about all of the subjects we've covered here.